Hello, and thank you for joining my poster session. Our research project is about the Alder-Towns effect in photoionization of hydrogen, and specifically contrasting the results of few-level quantum theory with ab initio numerical solutions. To begin, let's discuss the Alder-Towns effect. So field-dressed atomic states arise because electromagnetic radiation induces temporarily stable state configurations. A familiar example is the AC Stark upshift of all Rydberg level energies by the amount of quantum-motive energy, which is provided here. The Alder-Towns effect arises from resonant field excitation of bound states, and it results in the formation of quasi-energy levels that can only be detected by the application of a second field. The system under investigation in this work is hydrogen's 2p3d delta m equals 0 Balmer transition. And under resonant excitation, each of these energy levels split into what are known as Alder-Towns doublets, and these are separated by the Rabi frequency. The purpose of our study is to analyze the temporal and spectral consequences of an intermediate resonance en route to photoionization by solving few-level model equations and by ab initio numerical solution of the time-dependent Schrödinger equation, in both cases for hydrogen in 3 dimensions. So let's start with a 3-level reduction of hydrogen consisting only of the states of interest. So we consider the 2p and 3d bound states and one energetically distant continuum state labeled K. And a linearly polarized monochromatic field addresses the 2p 3d bound-bound transition and weakly ionizes it, transferring some of the population to state K. In this case, the dress level splitting is detectable in the photoelectron ionization spectrum. In other words, we anticipate that the absorption spectrum of the model continuum level K will exhibit resonances corresponding to the dressing of the bound states. The atomic amplitude equations are provided here in the Schrödinger picture. We factorize the initial state energy E2 and then consider a frame co-rotating with a field frequency omega. In other words, we invoke the rotating wave approximation. And the level frequencies and field interaction terms are defined here, and we have included an ad hoc ionization rate, gamma, to represent population loss to unmodeled states. Now we consider an approximate solution to this coupled set of amplitude equations. The ordinary Rabi solutions are employed for the bound state amplitudes, which is justified by the fact that the continuum level coupling V3K in the 3D state amplitude is negligible in comparison to the bound-bound coupling term V32. Substituting the Rabi solution into the continuum state amplitude equation, we find that CK may be written neatly as the sum of 2 terms provided here. The continuum occupation is the absolute square of this amplitude, which is plotted on the left here as a function of the energy difference between the 3D and the continuum level. And so in a theoretical framework, this absorption spectrum is what motivates the interpretation of field-induced level splittings. And you can see that the doublets are separated by the Rabi frequency. On the right, the time-dependent occupation probabilities of the model atomic levels are plotted. And as one can see, the bound state occupations oscillate at the Rabi frequency, of course, though now there's an exponential decay in total probability as a result of the model continuum level and its ionization term. Now we'll discuss the ab initio numerical approach to modeling the system. So the wave function is expanded as a discrete sum of time-dependent radial functions and spherical harmonics as shown. The time-dependent Schrödinger equation is written to its right, where dipole coupling with a linearly polarized field is included in the velocity gauge. And so the numerical calculation consists of time propagating each radial function using the Crank-Nicolson method. And since the field is linearly polarized, state transitions must leave the magnetic quantum number invariant, and they must change the angular momentum quantum number by 1. Now, for a given time step, the angle integrated spectrum is calculated from the expectation value of this second-order energy resolving window operator, which is associated with each radial function phi, and then summing the partial spectra as in this final expression. For the calculation, we consider a field whose intensity is 150 gigawatts per square centimeter and wavelength is 656 nanometers, which corresponds to the Balmer transition. And the atom is prepared in the 2p state via imaginary time propagation. In the first figure, we provide the electron differential energy probability density as a function of time. And so this is an all-encompassing view of the atomic level's occupation probabilities versus time. It shows, among other things, the 2p3d level Rabi oscillations, that's labeled A here, and the formation of above threshold ionization, or ATI peaks, which split into the Otler-Towns doublets over time, labeled by B and C. This is illustrated again in the second figure to the right, where we have plotted lineouts of the electron spectrum at different times. The signal in blue shows the energy distribution early in the process, where population is mostly contained in the 2p and 3d states, and there is minimal ionization. As you can see, at this time, there are only 3 ATI peaks, and their probability densities are orders of magnitude lower than those of the bound states. On the other hand, the final electron spectrum, once the laser pulse is passed, exhibits 5 ATI peaks that are split by the Rabi frequency, and that's shown here in red. So in other words, each ATI peak is now an Otler-Towns doublet. In summary, we have calculated an electron wave function's time-evolving spectrum with high resolution and accurately measured the degree of splitting in the Otler-Towns doublet. The solution was analyzed in both the temporal and spectral domains, and its results were contrasted with those obtained for a limited few-state analytic model. So thank you very much for your attention, and I would be happy to answer any questions.